Here we want to graph f of x equals x to the fifth minus 5x to the fourth. And for any graphing exercise like this, we'll use these 9 graphing guidelines. So let's just go through these in an overview before we take each one individually. We start with finding the domain of the function so we know what x values we're looking to graph over. Then we can take a look at symmetry, and honestly these don't have to be done necessarily in this order, though some things do need to be in order. But symmetry could really be done anywhere. The big deal is first and second derivatives, because from there we can use those to find the critical points and possible inflection points. So we're on to those are steps 3 and 4. Once we have those, we can use test points. That's the big deal, step 5, to figure out where we're increasing and decreasing and where the function, I guess, is concave up and concave down. Step 6, we can determine our extreme values, our maxes and mins, and our inflection points where it changes in concavity. Step 7, start looking at in behavior and asymptotes, anything like that. Finally, step 8, we get our intercepts. So a lot of people like to start with intercepts. That's just our x and y, where it crosses the x and y axis. And finally, step 9, of course, don't forget to plot the graph. Okay, so let's step through these. We'll start with domain. Well, our function is a polynomial, and all polynomials have the domain of all real numbers. So the domain here is all real numbers, which we can write as negative infinity to infinity. Step 2 is symmetry. So recall that for symmetry, we plug in negative x in f of x and see what happens. So here we go. Let's try it out. F of negative x. Okay, and if we get f of x back, it's even. And if we get negative f of x back, the exact same function, but we can pull a negative all the way out to the front, it's odd. Otherwise, it's neither. So let's see what happens in our case. F of negative x, okay, well that's negative, in parentheses, negative x to the fifth minus 5 times negative x to the fourth. Well, the first one, it's an odd exponent, so that just stays negative x to the fifth. The second one is even, so that becomes positive in there, but we still have minus 5, so negative x to the fifth minus 5x to the fourth. Well, this is not equal to f of x, and this is not equal to negative f of x, so this function is neither. On to step 3, first and second derivatives. In fact, I'm going to run through steps 3, 4, 5, and 6 for the first derivative and then come back and do all of them for the second derivative. That's a little bit more of an intuitive way to approach this. So we'll take the first derivative, and then from there we'll do our critical point, step 4, then to step 5, increasing, decreasing intervals, and then to step 6, our extreme values. And then come back and do the second derivative and go through all those steps again, get our inflection points, figure out where it's concave up and concave down, and that will tell us which of our possible inflection points were actually inflection points. So we'll do everything first with f prime of x. Okay, so I'm just going to put a little box around that. Let's see all the information we can get from that. Okay, well, the first derivative is not too hard to find. We just hit it with the power rule, 5x to the fourth minus 20x cubed. From there we get our critical points, so we'll set that equal to 0 and solve for x. Let's see, always factor out when you can, so let's factor out a 5x cubed, leaving us with x minus 4 on the inside equals 0, which we can solve for x equals 0 and 4. From here we want to do a sign chart where you essentially draw a copy of the number line and identify your critical points. So we have something going on at 0 and 4. And now we want to test a point in each region in between those points. So let's see here. So we'll test points here. So let's test x equals, how about negative 1? You can choose any point in the region you'd like. Between 0 and 4, let's choose 1. And then above 4, we'll do x equals 5. And we're testing these in the derivative because we want to figure out if it's increasing or decreasing in those intervals. Okay, so let's make a chart here. We have x, and here's our function, 5x cubed times x minus 4. And we just need to figure out if the value of x is positive or negative. So keep it keep the function in its factored form, and you just kind of do this very quickly. So let's see, we plug in -1 for x, 5x cubed, I don't know what that is, I mean I do, but I don't care, it's negative, times -1 minus 4, well, that's -5, so still negative. Negative times a negative is positive. Thus our function is increasing in that region, so I'll go back to my sign chart and put some pluses there, telling us that the derivative is increasing in that region. On to the next point, x equals 1. So we put in 1 there for x. Okay, 5x cubed, 1 is, when we put in 1 for x, it is positive. 1 minus 4 is still negative. Positive times a negative is negative. So it is decreasing in that middle region. So I'm going up to my sign chart, putting in negatives everywhere. Finally, we go to x equals 5. Plug it in. 5 cubed is positive. 5 minus 4 is positive. Positive times positive is positive. Back to increasing again for this last region. Go back up to the sign chart. Plus, 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 plus. So notice how this gives us a lot of information about our graph already. We can kind of see, you can imagine a graph that's increasing from -infinity to 0, and then decreasing, and then increasing again. So let's summarize our information so far from the first derivative. We have that the function is increasing from -infinity to 0, decreasing on the interval 0 to 4, and then increasing again from 4 to infinity. From here we can get our extreme points. We know from the first derivative test that when a function goes from increasing to decreasing, that gives us a local max. So we have our local max at x equals 0. But what's the y value? We have to plug back into our original function. So remember, our original function all the way back at the beginning of this was x to the 5th minus 5, x to the 4th. So f of 0 is 0. So we have our local max at 0, 0. Okay, then first derivative test again gives us a local minimum at 4, what? Well, plug into the original function, f of 4. It turns out that is -256. -256. So wow, really swam off to the deep end on that one. So we'll be adjusting the size of our graph here. So 4, -256. There's our local min. And that there is the essence of how to use calculus to graph things, right? This entire process we just did is what we'll do essentially for the first and then again for the second derivative every time we go to plot something. It really gives us a lot of information. It's a very powerful technique. Let's try it for the second derivative. First, recall that our first derivative, because it rolled off the page there, was 5x to the 4th minus 20x cubed. From there we can get the second derivative. So let's just denote this like we did before. So there's some separation here. Otherwise, as you can see, these problems do get pretty long. So do your best to organize them on your paper or tablet or whatever you're working on. Okay, again we get the power rule. 20x cubed minus 60x squared. And then we want our possible inflection points, so we'll set it equal to 0. Factoring out gives us 20x squared out to the front, and we're left with x minus 3. Inside equals 0. Well, how nice. That gives us x equals 0 and 3. For the x values for our possible inflection points. Let's use a sign chart to figure out if they are inflection points. And this will be analogous to what we did with the first derivative. So we draw our line here. We're going to define these regions. So here we have something at 0 and again at 3. Right, so I'm just taking big chunks. Next we'll test the points in the regions here. So let's test x equals, how about -1, x equals 1. I just like to choose the simplest possible points, and x equals 4. This region on the right, we could have just as easily chosen x equals 10 billion. We'd get the same answer, whatever it comes to. Okay, so there's our chart. Next, let's do our testing here. So I'm going to set up a little table here. X, and then I'm going to use the factored form because it's quicker to plug into. Again, we don't care what these values are, we just care if it's positive or negative for concave up and concave down. Now we run through each of those test points. So -1, plugging in here, -1 squared is positive, -1 minus 3 is negative, positive times negative is negative. So concave down, in this first region here, I'm putting negative, negative, negative onto my sign chart to remind myself of that. Next, plug in x equals 1. Okay, 1 squared is positive, 1 minus 3 is still negative. So interesting, it didn't change there, it's still negative. Negative, 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 negative. And finally, we'll plug in 4 for x. 4 squared is positive, 4 minus 3 is positive, so there we got a change. Positive times positive is, of course, positive. So now I'll go back up to the sign chart, plus, 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 plus. So it turns out that an inflection point occurs at x equals 3, but not at x equals 0, since the concavity changes at 3, but not at 0. But the name itself implies that we need a point, not just an x value. We know our x value is 3, but we need a y value, and remember for that we go all the way back to the original function. I think I have it here, right up here. F of x equals x to the 5th minus 5x to the 4th. When we plug that in, we get negative 162 for the y value. So there's our inflection point, 3 comma negative 162. Okay, we've come a long way. Let's check in with our guidelines to see where we stand. We have completed steps 1 through 6. Step 6 being to identify our extreme values and inflection points, which is the point of all that taking of derivatives, the first and second derivatives, solving for those values, checking the intervals. So next we're on to step 7, asymptotes and end behavior. So recall that our function is f of x equals x to the 5th minus 5x to the 4th. Here when we say asymptotes, we're referring to vertical asymptotes, but this is a polynomial, so we have none. So lucked out on that one. Just say none. Okay, end behavior, we are looking for the limits as x goes to infinity and negative infinity. So we have the limit as x goes to infinity of x to the 5th minus 5x to the 4th. Well, there we're really just looking at this leading term. And as that gets bigger and bigger and bigger, this is going to go off to infinity. So we have infinity off to the right of this function. And let's see the limit as x goes to negative infinity, x to the 5th minus 5x to the 4th. Again, we're only looking at the leading term here. And just imagine plugging in a very large negative number. That's how I always approach these. Just imagine what happens as we put in, say, negative 100,000. Well, it's going to be negative 100,000 to the 5th, which means it's still going to be negative. So that tells us this is going down in the negative direction, negative infinity. Back to the guidelines, we have arrived at our final 2 steps. Step 8, find the intercepts, and step 9, plot the graph. By intercepts, we mean x and y intercepts. Okay, so remember that when you want the x-intercept, you set y equal to 0. You always set the opposite variable equal to 0, essentially. So we're taking the whole thing. Remember, f of x and y are synonymous in this case. So 0 equals x to the 5th minus 5x to the 4th. Nice algebra. Here we go, 0 equals, let's factor out an x to the 4th here. Whoops, x to the 4th. Okay, x minus 5. So that gives us a 0 at x, 0 and 5. So there's our 2 x-intercepts, and then our y-intercept is even quicker. We set x equal to 0, opposite variable in this case. So essentially we're just evaluating f of 0, which is clearly 0. Okay, so we have our x and y intercepts. Let's pull everything together and sketch this function here. So there's our grid. We're going to need to go down pretty far here because there's a bunch of negative numbers. Okay, we have intercepts at x-intercepts at 0 and 5. 1, 2, 3, 4, 5. Okay, y-intercept is 0 as well. We already have that. It's concave up, so let's label these points 4, 5. We are concave down from negative infinity to 3, and then we are concave up between, I guess, 3 up to infinity. So I don't quite know what this is looking like, but we can get an idea of it. We'll slowly piece things together here. We have an inflection point at 3, negative 162, and then we have a local minimum at 4, negative 256. So let's just kind of label those points here. Negative 162 will be somewhere down here. Of course, this won't be to scale. And maybe negative 256 way down here. So we have a point here of interest, a point here. Don't forget our end behavior. As x goes to negative infinity, we're going down, and we're going up as x goes to positive infinity. So I think we have enough here to put all this together and sketch our graph. And I'll do a very rough sketch, and then I'll bring up the Desmos version so you can see what a nice one looks like. But I think we come up like so. We hit our local max here. We start coming down. We're concave down. All right, and then we switch to concave up. There's that second point, and then we go off to infinity like so. I think that meets all the qualifications. This is a little bit, this wavering in here isn't really the case because that's technically looking like it switches from concave up to concave down. So you have to be really careful when you sketch these. It's hard for me on this writing tablet. It's you always end up with these extra waves in the graph. So let's bring up the Desmos version and see what that looks like, just so you can see exactly what it should look like if you're drawing with a steady hand, probably on your own paper or on a whiteboard or something. Okay, there it is, the official function graphed. So it's always good to maybe check your work on something like Desmos and see exactly what it looks like, but we're very close, right? This is just a smoother version of it. But yeah, you can see all the points in there, the critical points, the inflection points, the intercepts. Yeah, everything works out. So these exercises are time consuming. Take your time, be careful. One of the more challenging parts of any course is the graphing, be it intermediate algebra all the way up through calculus. You always have to slow down a little bit when it comes to the graphing section and really make sure you understand all the steps along the way and create nice graphs that represent the functions we're looking at.